Good morning, everybody. So, yet again, I welcome you all to this lecture in fluid properties. So, today's lecture mainly devoted to effect of temperature and pressure on viscosity. Second, how you classify the fluids with based on viscosity. The classification of fluids based on viscosity, how we classify the fluids. That's a very important note that we will complete, and we will start some problems. And in the next lecture, we do more and more problems on this topic. Let us go into the topics of today. So today's discussion will be on effect of temperature and pressure on viscosity. Second is classification of fluids with examples. Then some problems. So if I take the first topic, what is the effect of temperature on viscosity? Already I mentioned to you that the effect of temperature on viscosity in liquids is different, in gases is different. So liquids, gases separately to be discussed. Again, in the previous lecture, we discussed what are the causes of viscosity. The causes of viscosity are: number one, cohesion; number two, molecular momentum transfer. So for liquids, viscosity is mainly due to cohesion. Whereas for gases, viscosity is mainly due to molecular momentum transfer, which is because of collisions. Hence, so if I study the effect of temperature, we need to study separately for liquids and gases. Now I take first liquids. In case of liquids, as the temperature increases, what will happen? Cohesion decreases because the attraction between the molecules decreases because as the temperature is increased, more and more molecules leave the space and the spacing between the molecules increases. As the molecular spacing increases, the attraction decreases. That is, cohesion decreases. So therefore, viscosity decreases. In case of liquids, as temperature increases, viscosity decreases. If you take gases, as temperature increases, collisions collisions increase. The molecular momentum transfer increases. Therefore, viscosity increases. So now if you take temperature, liquids, gases separately, so as temperature increases, viscosity decreases. As temperature increases, viscosity increases. So this is what you should know. So with this, I will go into the next topic. The next topic is actually the classification of fluids based on viscosity. Classification of fluids. So what is fluids are mainly classified into two types. Number one is Newtonian fluid. Number two is non-Newtonian fluid. First, what is Newtonian fluid? Fluids which obey Newton's law of viscosity. Newton's law of viscosity are called Newtonian fluids. That means what? Tau is equal to mu into dV by dy. So this law is obeyed. This is the thing. This law is obeyed means tau is proportional to dV by dy. Right? Tau is equal to mu into dV by dy whole to the power of 1. So therefore, the relationship in Newtonian fluids between shear stress tau and angular deformation or velocity gradient dV by dy is linear. Very, very important.
The relationship between tau and dv by dy is linear first. Here, mu is just a constant. This is the first thing you should remember. What are the examples of Newtonian fluids? Examples is water, kerosene, any light oils are all Newtonian fluids. Then what is non-Newtonian fluids? Non-Newtonian fluids. Fluids which do not obey Newton's law of viscosity are called non-Newtonian fluids. The subject related to non-Newtonian fluids is called rheology. We don't study much about this non-Newtonian fluids. In fluid mechanics, we confine ourselves mostly to only Newtonian fluids. Then again, these non-Newtonian fluids are further classified into number one, pseudoplastic fluids, number two, dilatant fluids, Bingham plastic, Bingham plastic fluids, then what we call it as rheopectic fluids, last thixotrophic fluids. So these are the five classifications in non-Newtonian fluids. So I will show you by graph and relations and at the same time the examples of each of these things. So for understanding better actually how we take up these things are just to draw a graph on x-axis rate of angular deformation or velocity gradient on x-axis and on y-axis the shear stress tau y, because on y-axis we have taken this is rate of deformation. You can also call it as velocity gradient. So first if I take it this x-axis, if I take it, what is x-axis? X-axis, if you see what whatever is the velocity gradient, whatever is the velocity, whatever the value of the velocity gradient, irrespective of the value of the velocity gradient, always tau value is equal to 0. Whatever may be the velocity gradient, right? Whatever may be the viscosity. So always tau shear stress is equal to 0. That is tau y is equal to 0. This is what we call it as ideal fluid. And this is possible only when mu does not exist. This is the first thing, x-axis. So the x-axis represents ideal fluid. This is the first thing you should understand. Then second thing, this is a linear graph. That means that linear graph basically, if you do write, I call it as one. The first one, if I take it, basically here, what it is. The first one is it obeys Newton's law of viscosity. That means what it obeys, tau is equal to mu into dv by dy. That is, tau is proportional to dv by dy. Then this fluid is called Newtonian fluid. So this first one you should remember, this is Newtonian fluid. Right? This is the first one. Then second one. So second one is, if you see how I am drawing. So this curve, if you see it, the second one is, its relation is non-linear. So that means it does not obey Newton's law of viscosity. Hence, non-Newtonian fluid. Again, in non-Newtonian fluid, how the relationship is, if you observe how the relationship is, the relationship will be like this. Tau is equal to some mu into dv by dy whole to the power of n plus b. This is how the relation is for non-Newtonian fluids. This is how the shear will be. Here, the value of n is equal to, the value of n is equal to, here basically how it will be, it is n value is less than 1. N is less than 1. And B is nothing but initial yield stress. Right? So for this type of fluid, if you see as the graph started from origin, initially the initial shear stress is 0. The initial shear stress is 0. Initial yield stress, sorry. initial yield stress is 0 and n is less than 1. So this type of things, what we call it as where this initial yield stress is 0 and n less than 1, and relation already I mentioned it is non-linear relationship. Non-linear relationship. The moment n is not equal to 1, it is only non-linear relationship. So again, what happens is when I say n less than 1 means actually viscosity decreases. Viscosity decreases with rate of deformation. And these type of fluids also called as shear thinning fluids. And all this corresponds to pseudoplastic. Pseudoplastic fluids. So pseudoplastic fluids means the first thing you should remember nonlinear relationship, non-Newtonian fluids, initial yield stress 0 and the index less than 1. So if that is the case, we call it as pseudoplastic. So what are the examples of this Eurostone? What are the examples? Mainly paints. Please note it. Paints, colloids, polymers. These are the examples for pseudoplastic fluids. So now let us go back and draw on the figure. So what this two is pseudoplastic. Then next, what is the what you call it as the third one? We will take it actually some different color. We will put it. We call it as 3. So I take it again. Third one. The third one is again, remember, this is called dilatant fluid. What are its characteristics? First one is it is non-Newtonian. Why non-Newtonian? The relationship is non-linear relationship. Relationship between tau and rate of deformation. And again here, initial yield stress is 0 and n greater than 1. N greater than 1 means actually viscosity increases with rate of deformation. These are called shear thickening fluids. The best examples for dilatant fluids are, right? The best examples for the dilatant fluids are suspended starch, suspended starch, basically corn flour, etc. Right? So what is the condition here? The initial yield stress tau is equal to 0. That is number one. And then basically the other one is what actually? Initial yield stress is 0 and n is greater than 1. This is what is the condition for it. So again, relation is nonlinear. So that is why let us write that also there for us quickly. This is dilatant, right? So two non-Newtonian, I have written it. In these two relations also graphs you see non-linear. Then next one is, let us take right one more color, something like it. So this is, if you see it, it is linear. I have drawn here. This you call it as 4. It is linear, but it requires initial yield stress. This is called actually Bingham plastic, right? So now that we will explain what it is. Fourth one, Bingham plastic fluids. It is again non-Newtonian fluid, linear relationship. Just because linear relationship, don't conclude immediately it is Newtonian. Even though relationship is linear, but initial yield stress is required. That is why it is categorized as non-Newtonian fluid. Linear relationship, right? Then, but requires initial yield stress for commencement of flow. Without that initial yield stress, flow will not commence at all. If you want to start the flow, initial yield stress is required. Then only we call it as the Bingham plastic fluid. So again, afterwards, for the mathematically, if I want to write this tau y must be greater than 0. Am I right? It is not basically 0. The initial yield stress is there, some positive value, then only flow commences. Then actually n value is equal to 1. So this is called Bingham plastic fluid. Example, best examples, always remember, you experience it. Toothpaste, unless you just press it, some stress is applied, it won't come actually. Toothpaste, that is one of the very drilling mud. This is another example, right? These are Bingham plastic fluids. Then what is fifth one? Rheopectic fluids. Again, it is a non-Newtonian fluid, non-linear relationship, right? Again, here how the mathematical equation is Again, before going into it, I will write initial yield stress is required. Initial yield stress is required. Without that, the flow will not commence. For starting flow, for starting the flow, and basically the n value is greater than. So mathematically, if I want to write the initial yield stress is required some positive value and n is greater than 1, we call it as rheopectic fluids. That is what the examples are. The best examples are bentonite clay. This is one type of clay. Bentonite clay, gypsum paste. So these are the examples of rheopectic fluids. So how that will be also, I will show you first in the graph so that we will be conversant with what we are learning also continuously. So this will be why rheopectic. The last one which we take it, this is the last one. This is thixotropic. And this is called as ideal solid. So last one we will let us behave, study the last one. 3, 4 is over, 5 is over, the last one. Thixotropic. So mainly in the case of thixotropic fluids, if I look into it, again these are all again non-Newtonian fluids. Non-Newtonian fluid, non-linear relationship. Initial yield stress is required. And n is less than 1. Relationship is tau y greater than 0 and less than 1. And the examples are basically blood, lipstick, then printer's ink, then yogurt. Then if you take ice creams, these are all examples of these thixotropic fluids. So finally, one conclusion, small conclusion, we will make it. So first classification we have made is Newtonian, non-Newtonian. So Newtonian is obeys Newton's law of viscosity. And that Newton's law of viscosity is tau is equal to mu into dV by dy. This is does not obey Newton's law of viscosity. Here tau is equal to mu into dV by dy plus whole to the power of n into b. This is called as power law of viscosity. Right. Again, in the non-Newtonian fluid, we have number one, basically, right? What is now dilatant? We have pseudoplastic, we have Bingham plastic, we have rheopectic, we have basically thixotropic. For dilatant fluids, if I take it first one, actually it is only tau y is equal to 0, and basically if I take it greater than 1, right here in that equation, this is tau y is equal to 0 and n less than 1, and this is tau y is greater than 0, n is equal to 1. It is linear relation, but this because of this it becomes non-Newtonian, and tau y greater than 0, n greater than 1, and basically last one thixotropic tau y greater than 0, n less than 1. So these are the five, and examples are very very important for this. So this completes to me the theoretical description of for the viscosity. But last, before closing this, once again, which I have explained to you already in the previous classes, what is an ideal fluid? Ideal fluid means viscosity mu is equal to 0, insignificant, right? If that is the case, if mu is equal to 0, whatever may be the value of dV by dy, shear stress is equal to 0. The resistance to flow is equal to 0. Kindly remember this. However, there is no fluid with 0 viscosity. Every fluid has some viscosity. To be frank, ideal fluid is a mathematical concept by mathematicians to analyze fluid problems. Else, practically all fluids are real fluids. But for analysis purpose, we consider water as ideal fluid because the viscosity of water is very, very less. You know it, viscosity of water is 1 centipoise, 1 by 100th of a poise, or 10 to the power of minus 3 Newton second per meter square. So that is why this is considered as, otherwise no. So all the fluids in nature are real fluids. What is a real fluid? So real fluid means it possesses certain viscosity. So hence resistance to flow is inevitable. Initially, when the fluid mechanics subject was evolved, the mathematicians has brought this concept of ideal fluid. But later, even whatever, whether it is water, air, which are considered as ideal fluids, there also we find so much of resistance. For example, an aircraft which is submerged in air and moving, it is experiencing resistance force. From where that resistance force is coming, if suppose air is viscosity zero, air viscosity is not zero, air is only, just for analysis we have taken it as ideal fluid, otherwise it is also real fluid, and basically it also cause resistance to the motion of the body. So similarly, a submarine which is moving underwater, it also experiences resistance. So that means water is also offering resistance. Why? Because it possesses certain viscosity, and viscosity gives rise to resistance to the flow. So this you keep it in mind actually. So with this, the whole thing of this chapter is completed. So kindly, very, very important topics we have covered in this. So some two problems I will introduce in today's class, and then tomorrow we will take up more and more problems on viscosity, because here, because the equation is only simple, there is only one equation which you use it for generally for solving any problems on viscosity. How but that equation is being used, that understanding is very important. So that's why each problem you think how that is being solved actually. So if I take the first problem, problem 1, if I take it, so what is the first problem which we are taking? Two horizontal plates are placed 12.5 mm apart. The space between them being filled with oil of viscosity (14 poise). Calculate the shear stress in the oil if the upper plate moves with a velocity of 2.5 meters per second. So this is the problem. So solution we will take it. So first what is given I take. The distance between the two plates is normally we call it as y. Y is 12.5 mm. So 12.5 into 10 to the power of minus 3 meters, because I always write in SI units quickly. Then the space between them being filled with oil of viscosity mu is equal to 14 poise. 1 poise is equal to, we know 1 poise is equal to, for example, 10 to the power of minus 1 Newton second per meter square. So this is our, always you should remember. So therefore 14 poise is equal to 14 into 10 to the power of minus 1 Newton second per meter square. This is second. What is the other thing? He wants shear stress. Then the velocity of the upper plate is 2.5 meters per second. Right? And what he mentioned, what you have to calculate, what is the shear stress? This is the question. So if you want me to draw a thing, so there are two plates. This is the one plate, and this plate is V. He has given it as 2.5 meters per second. The distance between these two plates is equal to y is equal to, this is 12.5 mm, and the space between the two is filled with oil. This is all oil. So this is oil, and its viscosity mu is equal to 14 poise. Right? So question is, what is tau? This is the question. So now naturally I will go only one equation I have, the Newton's law of viscosity. Newton's law of viscosity. That is the only equation I know. Tau is equal to mu into dv by dy. It is can also be written as tau is equal to mu into v by y. So see, all the data is given. So mu is equal to 14 into 10 to the power of minus 1 Newton second per meter square. Velocity is 2.5 divided by y is 12.5 into 10 to the power of minus 3. So please calculate how much you are getting. You please check it actually. If you check it, this will be around approximately, if you see, 280 basically. You will get Newton per meter square. This is Newton second per meter square into, this is velocity is meters per second. Second will cancel, and here it is y, it is meter. So here 1 meter, here 1 meter becomes 2 meters square actually. So it is finally becoming actually Newton per meter square. Right? This is the answer for the first question. Let me take one more question also and then stop here. Whatever problems I am taking are very, very important problems. Kindly remember that a rectangular plate 1.2 meters by zero point 0.4 meters, weighing 970 newtons, slides down a 45 degrees inclined surface at a uniform velocity of 2.25 meters per second. If the 2 mm gap between the plate and the inclined surface is filled with oil, determine its viscosity. This is the question. We will see. Solution. So what is given? Rectangular plate size they have given. Okay. Plate dimensions 1.2 meters into 0.4 meters. So immediately calculate the surface area. Is equal to 1.2 into 0.4 meter square. This is the first thing. Then second thing is weight. W weight is equal to 970 newtons. We will see what we will do. It slides down an inclined surface. Now let me draw. So this is a horizontal, right? How the inclined surface will be? This is the inclined surface. So this angle is 45 degrees, right? On this weight is there. This is the weight. Next, this weight is moving actually at a velocity of uniform velocity, constant velocity. This V is equal to 2.25 meters per second. Fine. Next, there is a gap between the two things. Here there is a gap. You see. So this gap is filled with, right, an oil. So this is an oil. And he wants what is this viscosity, right? This is the question. So next one is, this is the problem you remember. So then velocity is given it as 2.25 meters per second. Then always gap means this is what we call it as y is equal to 2 mm. Y is equal to 2 mm. I can immediately write 2 into 10 to the power of minus 3 meters. Now I will see what I can do. Let us think, right? The whole weight is like this. Naturally, the weight, how it acts, this is how the weight acts. The weight is equal to 970 newtons. The entire component of weight is not in this direction. What is in this direction is more important for us. You understand? Whatever is parallel to this inclined plane, the force parallel to the inclined plane is required for us. But weight is not acting like that. Weight is acting vertically. Now that is why we resolve its components. How to resolve the component actually? This is how the components are resolved actually. You right? This is the first component. This is. You followed? So now this is 45 degrees. So naturally this becomes 45 degrees. So this becomes W cos theta and this becomes W sin theta. So finally, what is the force with which this is moving? The weight component in the direction. Now this is the thing. Weight component in the direction parallel to the inclined plane is equal to W sin theta. This is very important. Not the total weight, right? So this is what we call it as the force. So what is the force component is equal to W is 970 into sine 45 degrees. Right? That we should keep it. That is first thing. Okay. Then what is the Newton's law of viscosity? Because finally I have to go over there on the Newton's law of viscosity. That equation is only required for us. What is it? Tau is equal to mu into dv by dy, or tau is equal to mu into v by y. What is tau? Tau is nothing but force by area. Which area? It is surface area. So how much is the tau is equal to for us? Tau force is equal to what it is the force W sine 45 by area is how much I have taken previously. You have calculated the area also. How much is the area which we got actually? 1.2 into zero point 0.4. So this is the first thing, right? If I take it, this is tau. Then V is equal to constant velocity 2.25 meters per second. Y is equal to 2 into 10 to the power of minus 3 meters. So if I substitute 970 into sine 45 degrees divided by 1.2 into zero point 0.4 is equal to mu into 2.25 divided by 2 into 10 to the power of minus 3. Right. Sine 45 is 1 by root 2 that you can substitute and then calculate all the things. So if you solve this, you will get mu is equal to, for example, how much you are going to get 2.54 Newton second per meter square. Very, very important question. An object basically moving on an inclined plane. Very important, very easy also. So kindly remember, this is one important question. So here not the total weight. only the here how it is acting also you remember. Suppose this is the plane, so your weight is like this, so weight is acting like this. So this component is trying to push, whereas the because of this oil actually oil offers resistance. This resistance is like that. When this is equal to this, then naturally this moves with uniform velocity. When this will move with uniform velocity, when this W sine 45 is equal to the shear force. So, right, then naturally this object, this complete weight is going to move with uniform velocity. So, as he has given, it is moving with a uniform velocity of 2.25 meters per second. Then I have taken W sine 45 is equal to basically what the force, right? That's why I calculated tau is equal to force by area. I put it and I worked upon that. So that's why this is how the W will be, and its components here it is W cos theta, right? This is W sin theta. So this point you should remember in such type of questions. So though I will stop the lecture at this.
Like, share, and subscribe. Hit the bell icon for more updates.